Welcome to the presentation of OptoSkin, a large-area, electrode-free optical tactile sensor designed for applications in robotics and interactive displays. This work was carried out jointly by the Institute of Solid-State Physics, University of Latvia, the French-German Research Institute of Saint Louis, France, the University of Ljubljana, Slovenia, and the University of Zaragoza, Spain, within the Horizon Europe Sestosenso project. Robot tactile sensing employs various methods, however. Touch sensing lags behind torque and vision sensing, limiting robots' cognitive abilities. Challenges include sensor complexity, robustness, and energy consumption. We are pleased to introduce our innovative solution, OptoSkin. It is based on time-of-flight principle, where light is used to localize the contact point. In OptoSkin, TOF sensor's light travels through the waveguide via total internal reflection. When waveguide is touched, light is reflected due to interaction with the environment, such as scattering by the skin causing frustrated total internal reflection, or deformation of the waveguide surface due to elastic materials causing FTIR and transmission pass blocking. The distance to the interaction point is determined by measuring the time required for the light to reach the interaction point and return to the detector. Using the known optical properties of the waveguide, together with the measured time of flight, the exact contact position can be calculated. Additionally, by combining the mechanical properties of the elastic materials with the measured deformation area, deformation depth, and time of flight, the applied pressure at the contact point can also be quantified. This combination of total internal reflection and TOF timing forms the core principle behind OptoSkin's touch and pressure sensing. To investigate both principles of the OptoSkin, two main prototype families were developed: hardskin and softskin. Hardskin uses rigid materials to study pure FTIR behavior. Both clear and scattering versions were tested to study the TOF signal. The laser-textured acrylic glass was also fabricated, introducing controlled scattering for reliable detection of different materials and colors in contact with the OptoSkin. Softskin employs deformable silicone, where contact causes a local loss of total internal reflection, allowing force-sensitive touch detection. Several OptoSkin demonstrators have been developed. On the left is the 3D printed hardskin mounted on the UR10 robot at ISL. It shows how the optical tactile sensing layer can be integrated directly on a robotic arm for interaction and safety testing. The second demonstrator is the optically clear and textured hardskin developed at ISSP. This version enables both high-quality optical propagation and controlled surface texturing to enhance touch sensitivity. The images illustrate the optical response maps obtained during interaction. The third demonstrator is the softskin developed at the UL. It uses elastic materials to achieve a compliant, soft interface capable of detecting touch, pressure, and deformation over curved surfaces. Finally, on the right is the mini demo implemented in Use Case 2 at Ocado. This setup integrates softskin of UL with a compact robotic platform, including embedded electronics and real-time touch detection for manipulation and handling scenarios. OptoSkin has several advantages respect to traditional touch sensors. For example, electrode-free design and fabrication flexibility. Sensitizing large areas with a few TOF streamlines electronics and reduces energy usage. Existing optical tactile sensors fall into three main categories: fiber optic, camera-based, and interferometric systems. Although highly sensitive, these approaches are typically complex, bulky, and difficult to scale, often requiring external light sources, cameras, or dense waveguide arrays. Unlike capacitive or resistive skins, OptoSkin is optical, transparent, and mechanically robust, with minimal wiring and low power consumption, suitable for both flat and curved surfaces. Further developments will focus on integrating faster time-of-flight modules with higher laser power and improved resolution into the waveguides, enabling higher tactile accuracy and increased sensing speed for OptoSkin. There are no existing solution combines TOF in tactile sensing, plus large area scalability in a single low-cost architecture. OptoSkin therefore has no direct competitors and represents a unique approach in optical tactile sensing. The OptoSkin technology has been recognized by the European Commission's Innovation Radar as a promising EU innovation. It is classified as a direct time-of-flight optical tactile sensor enabling large-area, electrode-free touch and pressure sensing. Its market maturity is evaluated as exploring, meaning the technology is actively developing and identifying value creation opportunities. The market creation potential assessment indicates that the innovation addresses the needs of existing markets and customers, highlighting its relevance for real-world applications. Thank you for listening. We hope you found this presentation insightful and engaging.